So, let us investigate about the flame temperature now. Okay, the flame temperature, we will try to take the maximum value. So, I have chosen the adiabatic flame temperature calculated using the full equilibrium model for different equivalence ratios starting from 0.7 to 1.4, which was the range which measure we actually showed the photographs. So, now please see this. At the equivalence ratio of 0.7, you have a flame temperature, adiabatic flame temperature itself without any loss itself, it is less than 1850 Kelvin. As the equivalence ratio is increased, you see a good increase in the flame temperature, and now at around equivalence ratio of unity, you see the flame temperature goes to about 2225 Kelvin, but it is not yet the maximum. Do you understand? So, when I say heat release from lean to stoichiometry mixture, what happens? The heat release increases from lean and reaches the maximum at the stoichiometry. That means the heat release is maximum at the stoichiometric thing. Then if you go to richer side, due to incomplete combustion, the heat release will slightly decrease. That means the maximum heat release is expected at the stoichiometric condition. But flame temperature also should follow that, no, but it is not. It reaches the maximum at a slightly rich condition. For methane, it is around 1.05, around that. So, this is 1.1. So, you can see that the maximum flame temperature is reached at an equivalence ratio slightly rich of the stoichiometry, that is 1.05 phi equal to 1.05. Okay. So, this is basically due to the fact that the thermophysical properties like thermal conductivity, specific heat, diffusivity, etc. depend on temperature, and how they vary with temperature dictate this maximum value, because thermal conductivity, specific heat, diffusivity, etc. will cause the flame to lose heat, correct. So, how they vary with temperature constitute the location of the maximum. Okay. So, in summary, I expect the maximum temperature at the maximum heat release, which is at the stoichiometric mixture. But both experiments as well as theoretical calculations show that the maximum occurs at slightly rich condition for methane air. This is because of the dependency of the thermal properties, thermal conductivity, specific heat, and diffusivity, etc. with respect to the temperature. Okay. So, this trend will be obeyed by the luminosity of the flame. For example, the luminosity is low at 0.7. Why? Because the flame temperature is much low. As I increase the equivalence ratio to 1, you are seeing the flame temperature increases. And at 1.1 also you can see that the flame temperature is almost same as that of the equivalence ratio 1. Correct, 1.1 and 1 almost same. So, when you go back to this, for 1 and 1.1 the same amount of brightness, a similar amount of brightness is seen. Why? Because the flame temperatures are almost same here. 1.05 are not done, 1.05 it should be slightly higher than 1 basically. So, the luminosity, the brightness of the flame exactly translates as this, and when you decrease the temperature at higher equivalence ratios, you lose your, lose your luminosity, the luminosity decreases. So, that is what we are trying to demonstrate here. Plus, now let us see how the laminar flame speed change with the equivalence ratio. Okay, starting from 0.7 here, 0.7, it is very low, it is just above 0.2 meter per second. Okay, so it is this is 0.25, so about 0.21 let us say. Then at the equivalent ratio of 1, it is around 0.4 for methane air. Again, methane air, it is about 0.4. Now, it is not maximum. It actually follows the temperature variation. Temperature variation produces maximum at a slightly rich condition, about 1.05. Here also you can see that around that value the maximum is attained. So, it is about say 0.42 meter per second, this value. So, why this is? Because SL follows TF. Primarily it is dependent on TF. That is why the trend of this SL variation with equivalence ratio follows exactly the variation of TF with the equivalence ratio. So, as a result of the temperature variation, laminar flame speed, which strongly depends on the flame temperature, we can theoretically show that. I will in the next slides I will show you that. So, since the flame speed as luminosity as indicated in the experiments, the flame speed also depends on the flame temperature. So, exactly it follows the trend of the flame temperature. Okay. So, SL attains the maximum value when phi is in the range of 1.05 to 1.1, which exactly the trend followed by the adiabatic flame temperature. So, this is for the methane flames. When we vary the fuels, we will see some trends which will show you. So, basically what we have to understand here is, there is if you have a methane or any other fuel in air combustion, the variation of the flame speed with respect to the equivalence ratio is such that the linear side, from the lean value of equivalence ratio, when the equivalence ratio is increased, the flame speed increases and reaches a maximum at slightly rich condition. This slightly depends upon the fuel. For methane it is slight, for other fuels it may not be, we will show you that. Then after reaching the maximum, towards the richer side, the laminar flame speed drops. So, now please see that this is the range of equivalence ratio where the flame is ignitable. When I extrapolate this curve, then at one particular equivalence ratio, you will see that the flame speed reaches 0 value. So, maybe it is 0 here, 0 value. That will be the limits of the flammability. Okay, we will also show you that. So, you understand that when the equivalence ratio is reduced further and further, the flame may not be able to propagate. So, this may be 0 flame velocity. So, that is the limit, lower limit and upper limit of the flammability in terms of equivalence ratio. So, now let us see the effect of fuels on the variation of laminar flame speed. Now, in this case, we have not put equivalence ratio in the x-axis, we have put percentage fuel in the reactant mixture. Basically, what we observe here is, let us take the straight chain hydrocarbons CH4 and C3H8. You will see that the variation trend is at, see for example, this is percentage fuel in the reactant mixture. That means the lowest value in the left side and the highest value, the lowest value in the right side indicate the lower equivalence ratio and the higher equivalence ratio respectively. And the flame speed increases from the lower equivalence ratio and reaches the maximum at a particular value of equivalence ratio, which is actually at the slight rich condition, and again decreases beyond the maximum value, where the equivalence ratio is now increased further from the rich value to the further rich values of 1.1, say for example 1.1 to 2.5 etc. Similarly, for methane we have already seen this. When you take CO, you will again see that the variation is in the lean side, it from a low value it increases and attains a maximum at a particular value, which is a richer value, and again further richer equivalence ratio, the flame speed drops. And for CH3, CH4, sorry, C3H8, CH4 and CO, C3H8, CH4 and CO, the maximum values of same order, say 0.4, 0.42, something like that. Small variations are there. But when you go to C2H2 acetylene, you will see that the flame speed is now very high, about 1.4 meters per second when compared to 0.4 for the straight chain hydrocarbon. You are seeing a very high flame speed because of the high reactivity. Again the same trend is followed, increase of the flame speed from the lean to the slightly rich condition, then decrease in the richer equivalence ratio. But the value itself is very high, the maximum value itself is very high for acetylene. Hydrogen on the other hand produces a flame speed of about 2.5 meter per second. So trends of variation of laminar flame speed with respect to the equivalence ratio or the percentage fuel in the reactor mixture is preserved for all the fuels. It increases when the equivalence ratio is less than 1 and reaches the maximum at equivalence ratio slightly more than 1 or more than 1, let us say, then further increase in the equivalence ratio creates a drop in the flame speed. So, all the fuels obey some trends, but the maximum values are different and the value at which this maximum is reached in terms of equivalence ratio are also different. Do you understand? So, the main thing is the flame temperature has some variation in these fuels, which actually depend on the properties of the fuel like Cp, K, diffusivity, etc. When you say diffusivity, there are three types of diffusivity. One is thermal diffusivity alpha, momentum diffusivity nu, and mass diffusivity. Okay, now if these are entirely different, then also there will be some effect of that on the variation of the adiabatic flame temperature or the flame speed itself. So let us talk about that in a bit. So the main summary of this particular figure is, you see that the laminar flame speed has a trend which is quite preserved for all the fuels. The maximum values are different based upon the reactivity of the fuel. Highly reactive fuels like acetylene and hydrogen have higher flame speeds, and the maximum value occurs at equivalence ratio, again depending upon the fuel characteristics. Now, some quantitative information for CH4 and C3H8, the maximum flame speed occurs at equivalence ratios of 1.08 and 1.2. You can see, 1.08, and for both it is about 1.08. For CH4 and C3H8, the maximum SL occurs at the equivalence ratio of 1.08. But for C2H2, it is delayed further to 1.2. Okay. So, as I told you, this is the characteristics of this. Properties of the fuel, how the adiabatic flame temperature varies and so on. Now, taking hydrogen, it is the maximum flame speed occurs at an equivalence ratio about 1.8, further shifted to the richer side. CO, it is also around 2. That means more richer mixture can attain maximum flame speed for H2 and CO. Okay, now another important point to note here is the occurrence of the maximum adiabatic flame temperature for other fuels, say CH4, C3H8, C2H2, etc., occurs at the same or not much difference in the equivalence ratio where the maximum adiabatic flame temperature occurs. But for hydrogen, basically, the adiabatic flame temperature reaches a maximum around a slightly richer side only, that is 1.07 itself, it attains the maximum value. On the other hand, the flame speed attains the maximum value of 1.8. Okay, so this is another shift. Do you understand? So already what we have seen is that the shift from the heat release becoming maximum at the equivalence ratio of 1. Attaining the maximum flame temperature, it is shifted slightly to the richer side. And for methane and propane, it is about 1.08, only slightly rich. When you go for C2H2 and CO, it shifts to 1.2 and 2 respectively. For hydrogen, even though we see that the maximum flame temperature occurs at 1.07 equivalence ratio, the flame speed becomes maximum at 1.8. This is because of the variation in the diffusivities alpha, D, etc. Or we can say that the Lewis number is significantly different from unity, which causes this shift between the adiabatic flame temperature and the flame speed itself. Okay, so more information you can refer textbooks on this. So, in summary, the maximum flame temperature tries to dictate the laminar flame speed, and the laminar flame speed attains maximum value in when the fuel burns in air at equivalent ratio which is more than 1. And these are due to the variation in the thermal properties of the fuel with respect to the temperature. And the shift between the flame speed and the temperature itself can be explained using the non-unity Lewis number. Now we move on to structure of a premix flame. Structure is nothing but the profiles. See, for example, I have a flame zone, a thin flame zone, which is propagating through the mixture. So, this is unburnt mixture, and this is burnt. So, now when I go from unburnt mixture, the temperatures are low. So, this is a T0, this is the temperature of the unburnt mixture. As I go like this, the temperature remains constant, and when I go very near to the flame, the heat from the flame heats up this mixture, and the temperature increases and reaches a particular value, and the reaction completes and it goes like this. So, this is the profile of the temperature across the flame. So, that is what I try to draw. This is our temperature. Now, at the flame it reaches a temperature say Ti, and here the flame temperature is reached. So, this is what I am trying to show here. So, this is actually the reactant side, unburned side, and preheat zone where the temperature can increase due to the heat conduction from the reaction zone, and this is the burned side. So, what happens? Unburned reactants have low temperature T0. It remains constant until it reaches the preheat zone where conduction from the reaction zone heats up this and the temperature increases. And at the boundary of the reaction zone, or the interference between the preheat and the reaction zone, you see that the reactants reach a temperature called ignition temperature, and the ignition occurs and the reaction occurs. That means the flame temperature increases further to Tf. Now, outside this zone is called recombination zone, where based upon the conditions, the temperature slightly decreases or remains constant. If it is adiabatic, it remains constant. So, this profile is actually called structure. Not only temperature profile, we can also have mass fraction of the reactant. Say Y reactant is the mass fraction of the reactant. So, the mass fraction of the reactant in the unburned side is say Y reactant, remains constant till some particular value. Then what happens is, at this point it diffuses to the reaction zone. So, due to the diffusion, its concentration or mass fraction decreases, and in the reaction zone it is consumed in the reactions, and within this, say maybe within a reaction zone, the reactants are entirely consumed. When the reactants are consumed, you can see that the heat release rate increases and reaches a maximum value at a point where the reactants are almost consumed. Then once the reaction is complete, because of the consumption of the reactants, the heat release rate drastically drops to 0. So this is called the structure of a flame. That is, when you go perpendicular direction to the flame, how the quantities like temperature, reactant concentration, heat release, or you can also do product concentration, etc. vary. That profiles indicate the structure of the flame. So that means when the premixed reactant approaches the flame in the direction normal to this, as I shown here. So here the reactant approach normal to this, the temperature of the reactants increases from T0 to a value of Ta, which we call ignition temperature. Now this happens in a zone which we have named as preheat zone, because the reactions are preheated in this zone. Now next to this, the reaction, all the reaction takes place. This is called reaction zone. Very small thickness, even though I have exaggerated it, it may have a thickness of about 1 mm, 2 mm, etc. Order of a millimeter, we can say. Now in this zone alone, we see the bright or luminous bright color of the flame. The zone where the reaction takes place and heat release is complete, that zone is the reaction zone where the luminosity is displayed based upon the temperature value. So due to reaction, temperature reaches the maximum value or the flame temperature value, and then the recombination zone, further burning of a rich mixture takes place, or the flame plume, the gas go away, basically burnt gas go away, and the flame temperature based upon the heat loss, it will decrease or remain constant. So this is the structure of the premixed flame. So careful measurements have to be taken, or numerical simulation has to be conducted using detailed chemistry in order to get the structure of this particular flame. So now let us consider the mechanism in which the reaction zone and preheat zone interact. As I told in the previous slide, the first thing is the heating up of the reactants in the preheat zone. That means due to heat transfer from the reaction zone to the preheat zone, the temperature of the reactants increase. Similarly, the reaction zone, we have seen in the kinetics lecture that the initiation, branching reactions or propagation reactions will form radicals like OH and OH. This also will go from the reaction zone to the preheat zone. The radicals also will diffuse from the reaction zone to the preheat zone. So this also will initiate something in this. So you can see a slight heat release rate in this zone. This is because of some initiation of the reactions in the preheat zone, towards the end of the preheat zone, which is due to the transport of radicals, and temperature being somewhat higher, some radicals are transported, so there is a heat release which is occurring. But major reactions complete in the reaction zone only, as shown here. Okay. So radicals like OH and OH form in the reaction zone, and they are transported from the reaction zone to the preheat zone. The reactants heated to the ignition temperature will react with the radicals, and chain initiation reaction can take place. Okay. Now more radicals can also produce in this zone, and chain propagation and chain branching reaction can be facilitated due to this in the reaction zone. Okay, so it's not only the heat transfer from the reaction zone to the premix zone, it is also the radical transport from the reaction zone to the preheat zone, which keeps the flame to propagate over the unburnt mixture. So, for lean to stoichiometric mixture, reduction in the mass fraction of the reactants and rise in the temperature in the reaction zone causes or is caused by this both the effect of the temperature diffusion or the conduction as well as the radical diffusion. When the reaction proceeds, the reactants are consumed. Okay, so please see here that this fall of the reactant mass fraction is due to diffusion of the reactants towards the reaction zone, and this fall is due to the reactants participating in the reaction itself. So, as the reactants are consumed, they are consumed in the chain termination reactions, and heat release also after reaching the maximum decreases as the reactants are consumed. So, the major reactant species are consumed, the heat release decays to zero rapidly. So, this is what the structure is explaining us. Now, how the diffusion flame can be formed around the premix flame? That is due to the recombinations of the species in the downstream of the reaction zone. So, for example, the preheat zone and the reaction zone and the recombination zone. Now, in this, after reaction is complete, see for example, if there is a unburnt mixture here, which is basically rich, okay, say 1.5 equivalence ratio, something like that. So, what happens is in the reaction zone, this is premix reaction zone, correct? Only given amount of fuel which has enough oxidizer to burn will burn. The fuel species can come out here in the recombination zone and they can burn. This is the extra fuel which burns taking the atmospheric air. So, this is the formation of the diffusion flame. Okay. So, downstream of the reaction zone, recombination of species occur. Depending upon the initial composition, this zone can have another flame, diffusion flame, or if the equivalence ratio is say less than 1, then it will only have the burnt gases. Okay. Now, intermediate species are formed towards the end of the preheat zone and consumed before the end of the reaction zone. That is, intermediate species means apart from the radicals, you have metastable species, etc. That will also form and consume within the reaction zone. Okay. So, diffusion flame is formed only in the case where the fuel elements come out due to the richness of the unburnt reactant mixture. Now, flammability limits. Let us take an isolated system when the fuel and oxidizer are mixed in proper proportions and ignited using a localized high temperature, then a sustained reaction may take place. What is isolated system? I don't allow for any mass transfer. No further fuel or oxidizer can be allowed inside. So, whatever be the mixture which I first send in, that is the composition of the mixture itself. Now, based upon the composition, upon ignition using a high temperature zone, you cannot create sustained reaction until the mixture is itself flammable, because that means if it requires more oxygen or more fuel, it cannot ignite because we are isolated the system already. Now, the flammable mixture is one which can burn without requirement of extra oxidizer, which is not actually available now, or extra fuel. That means if the mixture has certain amount of fuel and oxidizer, if it can burn without having the requirement of additional oxidizer or additional fuel, then it is called flammable mixture. That means the mixture itself is within the flammability limit. Okay, this again gives us that for all the fuels we cannot define this limit in a unique manner. The flammable mixture is defined dependent on the type of fuel or oxidizer itself. When you use air as oxidizer, you have some flammability limit. On the other hand, if you use pure oxygen as the oxidizer, you have certain flammability limits. Similarly, for methane, there will be a flammability limit in air and in oxygen. For hydrogen, it will be very wide, considering both air and oxygen and so on. So, that means both the type of fuel and the oxidizer can help us or can make the flammability limit to be in a certain range. Apart from this, temperature and pressure of the unburned reactants can also vary the flammability limits. So, okay, what is limits of flammability? What is the mixture which has, say for example, let us take a mixture in which the mixture is first lean, that is more oxidizer is present and some amount of fuel is present. It is a lean mixture. That constitutes a lower limit. When if this particular mixture with more oxygen can ignite, then that constitutes to the minimum limit. That is, if you increase more like the oxygen or oxidizer slightly more, then it will not ignite. That is the what we can say is the maximum oxidizer that can be present in a mixture which can ignite is the lower flammability limit. Similarly, the maximum amount of fuel that can be present in a mixture that can ignite is the higher flammability limit. For determining this, we have standard test procedures. Okay, now let us go. I will just tell you about the standard test procedure. So, the standard test procedure will be like this: a long tube in which I can supply the fuel plus oxidizer, whatever I want in whatever proportion, say phi, whatever unburned temperature Tu I do is, and that is a spark igniter. Now I ignite this and a flame forms and it propagates through a particular distance. The flame has to form and propagate through a particular height. Then the test is passed. That is, we can declare that the mixture of this equivalence ratio is flammable for the given fuel and oxidizer. There is another setup in which I have a spherical vessel and I inject the mixture here, and again the spark plug is kept here, and at the center I try to ignite, so that a spherical flame is formed, and if the spherical flame goes over a 90-degree range, then I say it is flammable. So, these are all standard test procedures in which I try to create a flame, allow it to propagate through the particular distance or particular angle, so that I say that the particular flame mixture is flammable given its equivalence ratio, type of fuel, oxidizer as well as the Tu. Okay, how this is going to vary we will see later. Okay, so standard test procedures are used to determine the flammability limit, and this is very important information for us to design the explosion vessels and vents. So, I will stop here. I will continue tomorrow.